doing a one-way ANOVA test. In our example here, we have one factor, so we're looking at fertilizer. There are three different brands of fertilizer, so we want to see if the brand of fertilizer makes a difference. So there are three levels, one factor, three levels. So we do a one-way ANOVA test. The sample sizes for A, B and C do not all have to be the same. We are assuming that the yields are normally distributed, and that's one of the conditions of the ANOVA test. So H0 and H1. So H0 is stating that the yields produced by all three fertilizers is the same. So there's no difference between the fertilizers. From the formula book, we have to do these two calculations. And then we produce a table called the ANOVA table. This is the core of the ANOVA test. All our calculations will feed into this table, eventually working out our test statistic here. So the total sum of squares, SST, from this formula goes here. The between sum of squares will go here. And then these two values add to give this total. So we can work out this missing value. So fertilizer A, if we add up all the values, the total for A, 122, and there are 5 values for sample A. And doing the same for B and C. The total of these is 602. There are 18 values in total in the whole table. If every value is squared and then added together, sigma x squared is equal to 21974. The total sum of squares, so from the formula book, substituting the values in, gives us this. The between sum of squares gives us this value. In the calculation, we need to do this part first. Sigma t squared over n. We need to do each sample separately. So, sample A, the total is 122, and there were 5 values in that sample. T squared divided by n, 122 squared divided by 5. The next one, 296 and 7. So t squared over n, 296 squared over 7, and so on for the third sample. And then we've got this, minus t squared over n. The t here is this value. N is 18. So t squared over n, 602 squared over 18. And then we get the between sum of squares value. So in the ANOVA table, we've got these two values. We know that these two add up to give the total. So we can work out the missing value easily. For degrees of freedom, For the total, it's n minus 1. N was 18, so we have 17 degrees of freedom. For between degrees of freedom, we have 3 samples, A, B and C. So 3 minus 1, 2 degrees of freedom. Or we can say there's K samples, K minus 1, 2 degrees of freedom. And once again, the missing value here, 17 minus 2. Moving on to the mean square, we have to divide these two values. And then again, dividing. The sum of squares divided by the degrees of freedom, always in that order. And finally, to work out the F ratio, we divide these two values. And in that order, between divided by within, to give us our test statistic. To get the critical value, we need to go to the F distribution tables, and the degrees of freedom, there's two values that go in here for degrees of freedom, and it's always in this order. The top one first, and then the bottom one, 15. When we divided the mean square values, we did this one divided by this one. So when I'm looking up the critical value, it's this one first and this one second, F2, 15. We're using a 5% significance level. It's always a one-tailed test. All ANOVA tests are one-tailed. So now we can go to the F distribution tables in the formula book. 3.682 is our critical value. So 8.97, the test statistic, is greater than the critical value, 3.682, so we're going to reject H0 and a conclusion in context.